talking about transient deep learning as a method for malaria detection. As many of you know, malaria is a life-threatening disease which actually transmitted by two people through the bites of infected mosquitoes, and early detection of this disease is actually vital for survival. Right now, the method of diagnostics is very laborious and inefficient. So, physician actually looks through the microscope into the blood smears and inspect each of a blood cell and see how many of them has like a blood parasite there, and makes the diagnosis like that. So, needless to say, there is a lot of misclassification and errors and human mistakes in this approach. That's why it is good to actually have some kind of machine learning approach, particularly deep learning, here to reduce all of these problems. So the data set I will be using is the NIH provided data set, which is a National Institute of Health. Currently, data set has 27,000 cell images of blood cells. And as you can see, there are only two levels which are actually well balanced. As you can see from these images, the dots here represent actual parasite infection. So it's actually not that complicated to see if the cell is infected or not. So as a convolutional body for the transfer learning method, I will utilize MobileNet. There are two reasons for that. First reason is it seems like MobileNet is suitable for mobile devices, and it was created for mobile devices mostly. And in some applications, they said that the model actually outperformed other architectures like SqueezeNet, AlexNet, or Inception, and it also quite efficient, as you can see from this table. So it does not use a lot of RAM, so that means it could be used in some kind of portable devices, and those portable devices would be very efficient in rural areas for malaria detection, where there is no internet, and it actually can detect it on offline. And the second reason is actually through the publications was a lot of VGG and ResNet and AlexNet application to that problem, but no one actually took MobileNet as a detection tool. So it was kind of interesting how such a lightweight architecture will perform in this kind of problem. So I used as a head for this. So for this problem, I used very simple head, which includes average pooling layer, dense layer, and two dense layers basically. One dense layer with 112 dimensions, one with one dimension for classification. And the initial model actually did not perform well. It actually showed a lot of signs of overfitting, as you can see here. But the accuracy actually was quite good from the start. It was like about 92% accuracy. So I also inspected for the actual base model. I actually expected each of the feature map layer, and I have tried to check what the filter might look like for each of the infected cell. So basically how the network detects the cell. And as you can see here, it seems like for the first layers are very efficient in terms of detecting the parasites. So you can see the parasite edges could be seen here very easily, while on the last layers, the picture beginning to deteriorate, and you cannot actually see what it is doing. So it kind of becomes more specialized for that detection. It might be not very efficient for this kind of classification case. So because the model is overfitting, I try to use some kind of hyperparameter tuning and also model fine-tuning. So for fine-tuning, I used multiple layers, and actually top layers did not provide me a good model. In fact, some of the models were actually were deteriorating my. In fact, some of the models actually were corrupting my current model, and because I tried 3 different models from different layers, close to the middle was more efficient to learn efficient parameter. To learn, it seems like the layer close to the middle gave a good performance for the overall model. As for hyperparameter tuning, I used grid search approach, and I was TensorFlow variant of grid search. And I used different optimizer, dropout rates, and L2 regularization for that, and I found some parameters. So the dropout was actually, the dropout I used was quite extreme, was 0.5, and regularization was 0.7. And with those parameters, the model started to converge easily and without big overfitting. You can see here it's kind of still a bit overfitting, but close to the end, it is actually converging very well. And this dropout rate actually agrees with other publications where other authors indicated that they use some kind of extreme dropout rate to overcome these overfitting issues. So another approach to tackle this overfitting problem is that data augmentation. So I used random horizontal flips, vertical flips, random image crops, and rotations to reduce the overfitting, and it seems like it worked a little bit. So the model bumped up a little bit in terms of accuracy. So eventually I was able to get something like about 93% out of testing and training, which is. There is one more interesting observation which I found in a classification. Unfortunately, I did not add it to my report for these images. Some of the false positives has actually some kind of signs of parasite infections, and I confirmed from the literature that some of those labels were actually mislabeled in a data set, and the neural net actually was able to classify them as a malaria anyway. So it seems like the model performed even better than it's supposed to be. So as a summary, the base model performance was quite good. Wasn't as good as ResNet, which was selected as a top choice for this particular problem in other publications. But I believe that if you use some regularization methods and other optimization techniques, the model performance could be as good as close to the ResNet performance.